and rate of change, day 5. Yesterday we talked about average rate of change and instantaneous rate of change. In review, the average rate of change is a secant line. You got 2 points, and you want to find what is the average rate of change between those 2 points, or what is the average velocity. And to do that, you're going to do change in y over change in x, or change in position over change in time. Coincidentally, it also gives us average acceleration if we're starting with the velocity function, because change in velocity over change in time is acceleration. And then we also talked about instantaneous rate of change, where we take our secant line and we let the 2 points on each side get closer and closer to each other until we have a tangent line. And that leads us to instantaneous rate of change. It is calculated at a single point. It tells us the velocity at the single point. Or if we start with velocity, it tells us the acceleration at that single point. Velocity is the slope of the tangent line for a position function. Instead of doing delta y over delta x, because delta x has approached 0, we'll say dy dx. That's our derivative notation, or we can use our definition of derivative. So today we're going to have a few practice problems with this to review. Suppose that y equals x squared plus 1. Find the average rate of change of y with respect to x over the interval 3, 5. Average rate of change of y with respect to x, that means dy dx. Or, since it's average, delta y delta x. All right, so delta y, delta x. Well, change in y, we're going to do y evaluated at 5 minus, y evaluated at 3 over 5 minus 3. Y of 5 is 25 plus 1, which is 26, minus y of 3, 9 plus 1, which is 10, over 2. 16 over 2 is 8. There's no units on the question, so I don't need units on my answer. For B, find the instantaneous rate of change of y with respect to x at the point x equals -4. So this, because it's average rate of change, instantaneous rate of change. I was trying to change my incorrect work on the first one to be correct while thinking about the next one. Because it's instantaneous rate of change for B, it'll be dy dx, which is our derivative. So I'll take the derivative of my function, 2x, and I will substitute in my point. The derivative of y with respect to x when x equals -4 is -8. So the average rate of change from 3 to 5 is 8. Find y of 5 minus y of 3 over 5 minus 3 and simplify. And the instantaneous rate of change at -4 is -8. You take your derivative and substitute. For number 11, in no particular order, we have a graph that shows position versus time. So this is a graph of position. Is the particle moving faster at t sub 0 or t sub 2? Well, moving faster, that's speed, velocity. Velocity. All right? Velocity when given position is a derivative. So we're saying which one has a higher derivative or a slope of the tangent line? So let's roughly draw these in. Here's our tangent line at t sub 2. Here is our tangent line at t sub 0. Well, which one has a higher slope? Well, the derivative at t sub 0 is greater than the derivative at t sub 2 because the tangent has a steeper slope at t sub 0. Question B, at the origin the tangent is horizontal. What does this tell us about the initial velocity of the particle? Well, the tangent is horizontal. What does a horizontal line look like? It's a flat line. What's the slope of a flat line? Well, the slope of a flat line is 0. So if it has a horizontal tangent at the origin, the initial velocity is 0. Is the particle speeding up or slowing down from 0 to 1? Well, let's evaluate what's happening at t sub 1. There's our tangent line. Did it get steeper or less steeper? Well, it got steeper, so the particle is speeding up. What's happening from T1 to T2? Again, we can look, we can see, evaluate the steepness, and we can see from T1 to T2 it slows down. There's more to that problem we could evaluate when we start discussing concavity in chapters 3. But for now, we can just compare the slopes that it starts with and the slope it ends with. And the last question we'll look at today, a particle moves on a line away from its initial position, so after t hours, it is s equals 3t squared plus t miles from its initial position. Find the average velocity of the particle over the interval 1 to 3. Again, average velocity is change in position, so it'll be s of 3 minus s of 1 over 3 minus 1. 3 minus 1 is 2, s of 3. 3 times 3 squared, 3 squared is 9 times 3 is 27, plus 3 is 30, minus s of 1. 1 times 3 plus 1 is 4. So we got 26 over 2, which is 13 miles per hour. Units in the question are miles and hours. For part B, find the instantaneous velocity at t equals 1. Instantaneous velocity is the derivative of position. So that would be 6t plus 1. So at time t equals 1, our velocity is 7 miles per hour. So in review, the average rate of change of a function is the slope of the secant line. Change in y over change in x. And that is the average rate of change. The average rate of change of velocity will give us average acceleration. For instantaneous rate of change, what we're finding for instantaneous rate of change, we let the 2 points approach each other and we end up with the derivative. The derivative of position is velocity. The derivative of velocity is acceleration.